Okay, thank you. Hello, everyone, and good evening. Uh, the goal of this work is to find which grade reduces wear risk under realistic loads and speeds, and is to know if the upgrade from L-80 to P110 is worth it or not. Okay. My name is Iman Onsa, and I'm a PhD student at King Fahd University of Petroleum and Minerals in the Mechanical Engineering Department. Uh, Here's the outline of what I will say. I will go through each point of this during the presentation. So to start, I have a few key definitions, starting with the casing, which is a large steel tube that supports the wall of the oil and gas wells, which you can see here. And the tool joint is the thickened part of the drill pipe, this one, um, which connects the drill pipes together. The wear happens in the contact surface between the casing and tool joint, and it's mainly driven by the contact and sliding. And now for the casing wear. Casing wear is a loss of wall thickness in the inside of the casing due to the friction between the tool joint and casing. And to analyze this, I have used finite element methods, which is a numerical technique to divide a structure into small elements and solve for the real world problems. Okay. The consequences of casing wear can be divided into structural and economical. In structural, we lose the wall thickness and strength, which reduces the safety margin. And economically, wear can lead to expensive repairs or early abandonment of the well. Wear is driven mainly by three factors. The first one is the mechanical contact. This is when the tool joint presses against the casing. And the second is the relative motion by rotation and sliding of the tool joint. And the third is the drilling fluid and friction, meaning the mud pipe determines the coefficient of friction and can introduce abrasive particles. Yep. There is few wear mechanisms that are involved in the microscopic level, starting with the abrasive wear, which occurs when hard particles or asperities cuts and plows the softer casing surface. And the second one is adhesive wear, which happens due to micro junctions forming and breaking between the two surfaces. And over many cycles, fatigue wear occurs due to repeated loading, causing small cracks on the surface. Okay. This work is mainly based on published work, which was done here in the university, in King Fahd University, which was an experiment of the contact between the casing and tool joint, which had many problems. Firstly, that it was so time consuming and it was very expensive to set up for the experiment. And also there is some flying debris from the wear particles, which was a safety hazard. Also, the wear factors that used by engineers are very generic, and it was only from the dry conditions. And this project is very important because the wear had a huge impact in the environment. If the well is destroyed, then the oil will spill everywhere. And then finally, for this project especially, we wanted to compare between the different materials at different loading conditions. The objective is to build a finite element model for casing wear, and then to validate it against experimental data for L-80 steel. And after that, compare the wear between L-80 and P110 to see which is more wear resistant. So to start, I have modeled a 3D model of the small section of the casing and tool joint with a thickness of 25 millimeter to replicate the experimental setup. The material properties I have used for the casing, one's L-80 and the other P110, with the standard material properties, and for the tool joint is a high-grade alloy steel. And we can notice that the hardness of the tool joint, of course, it's harder than the casing, but the P110 is much higher than L-80 steel. And we will talk about it more later. The mesh was done in 5 layers to see the wear depth, and the element size was 3 millimeter with tetrahedrons and linear order, with these total number of nodes and elements. A mesh sensitivity test was done to make sure that the 3 millimeter size is appropriate, and comparing the stresses at different mesh size, we found that it's more stable between the 4 to 1 millimeter, in which we can see that the 3 millimeter is a good size. The boundary conditions applied are the rotational speed or angular velocity to the casing of value 115 RPM and 200 RPM, 207 RPM from the experiment, and force of 1000 Newton and 1400 Newtons, while fixing the outer diameter of the casing. Throughout the whole simulation, the force was fixed at its value, while the angular velocity was ramped up for a few microseconds, and then it was stabilized at the constant value. The simulation was done as explicit simulation, which means that we can take results from few seconds to replicate the whole experimental time, which was 190 minutes. The wear law implemented in the FEA simulation was Archer wear law, which indicates that the wear depth has a relationship with the wear coefficient and sliding distance. The wear coefficient is related to the hardness, while the sliding distance has a relationship with the rotational speed time. And this law was implemented in LS-DYNA, which is the explicit program to simulate by the contact automatic surface to surface, in which we have to indicate the master surface in contact and the slave. The master, of course, it's the harder material, which was the tool joint. The algorithm used for the contact is the penalty methods, which treats the contact stiffness like a spring to prevent penetration, and the coefficient of friction applied to the contact surface is 0.23 for the water-based method. Archer wear law is implemented by the keyword contact add wear, in which the zero means the Archer law, and the first wear parameter is the wear factor, and the second one is the hardness. The assumptions for the simulation is that the tool joint is rigid body, meaning it has no deformation. and the coefficient of friction in the contact area is constant throughout the whole runtime, which is 0.1 seconds. And we assumed constant operation conditions, and there is no temperature effect. And most importantly, that the wear has a linear relationship with time. Okay. The results, after we took the results from LS Dyna, it was imported to LS pre-post to see the results from the function of Archer-Weir law. And then we calculated the Weir values and scaled it to the whole experimental time, meaning the 0.1 second will equal the 190 minutes, and then we validate it against the experimental data. Before that, the stress analysis was done. The results
Iman,
from... Yes?
you have just 2 minutes left. I'm sorry to interrupt.
Okay, fine. The results, the stress from the simulation was much higher than the yield stress, which means the material has exceeded the yield point. Also, the material shear stress is higher than the shear stress from the simulation is higher than the material shear stress, which means that the material has exceeded the shearing point. Okay. The resulted value from the simulation give us the weir depths of 0.3 millimeter weir depths, while the experimental was 0.355, which gave an error of only 12%. And the sliding distance of the simulation was 71 millimeter, which gave an error of only 4%, which means that we can rely on the simulation instead of the experiment. Here is the side view of the simulation. This is after 0.1 second, and that of the experiment after the 190 minutes. We can assume that the 0.1 second is equal to the 190 minutes. Okay. Now, finally, after we made sure that the simulation can be correct or compared to the experimental, the material was changed from the L-80 to P110. And we know that from earlier that the hardness of the P110 is higher than the L-80 steel, which gave a weir depth less than the L-80 steel at low speed and high load of 115 RPM and 1,400 newtons. While under high rotational speed and low load, the difference was less, which means that the force is more dominant in the weir depths. So for conclusion, we can conclude that the FEA can be used to replicate real life problem and can be used for weir simulations, and that we can assume that the weir depths has linear relationship with the time, and that the P110 showed a less weir depth than the L-80 under severe conditions. And the recommendation, we can consider that to use P110 instead of L-80 because it was better under the different conditions. And for the future, we can include the thermal effects and assume the non-linearity of weir. Okay. Thank you.